True. I mean, I snuck it to like one of the casinos when I was like 17. So I just like left like after time like pretty cool though. I like a fun high school experience. I would have forced to school. Let's just say that.
Okay. So, I will get a new homework posted on this page this evening or Monday. But there's this first set, I've got a few coming in a little later, so I was waiting till I got all of them. So Hamilton, right? Okay, so Hamilton was a mathematician. He was an Irish mathematician, and he actually did quite a few things in mathematics. Well, one of the things he's famous for. So he's also famous as like an alcoholic. I don't know famous alcoholics, but he drank a lot. And so there's a story of him writing this equation here, like scrolling it onto a bridge. That's cobblestone on one of the bridges.
Just see the message.
You can't hear anything? Can you hear? Hello? Ah, it's the worst. Yes, we can hear. Okay, good. Thank you for that. So anyway, so I was telling a story to those that are online that Hamilton scrawled this set of equations onto a bridge. This set of equations defines the quaternions. I was going to say something about this historical interest, but also present interest. These equations here. I think probably some of you know. How many people have heard of the quaternions? Anyone? None? Anyone raising hands online? Probably not. Why can't be full screen? Is it strange? I'm used to seeing it. Okay. So how many of you have heard of like whole numbers? Okay, good. So natural numbers? Just, how do people think of natural? What are you guys taught about natural number? What's a natural number?
I took that class like 5 years ago.
You took a class on natural numbers?
I know, I heard about it 5 years ago.
Okay, okay. What,
Any normal number, 1, 2, 3.
1, 2? But is 0 natural?
I don't think so.
No, I don't think 0.
Zero's a whole number. So the French would say 0 is natural. And I'm like a Francophile, so I include 0. But I know in America, things are different. So. How about these guys? You guys know about these guys? Integers? Right? You have the integers, they have like all of the natural numbers and then the negatives and 0. You didn't include them. This is contained in this. So the integers solve an equation like x plus 1 equals 0. That can't be solved here. It can be solved here, right? X equals -1. You guys know what this is? I should know all this because you'll have kids someday, maybe. You shouldn't necessarily. You can have, yeah, don't feel pressured, thank you. Don't feel pressured. Have kids whenever you want, if you don't. If you want. They're great, I like kids. I like my kids. I love other kids. What is it, Q is? It's called rational numbers. You know about, now you know that. What is a rational number solves another equation. So this solves this equation. I'd like 2 times x equals 1. Right? You know what I'm talking about? What's the solution? 1/2. And like intentionally muffled. 1/2, correct. Well, 1/2's not an integer, right? It's rational. Good. There you go. See. All right. No applause. Hold your applause till the end. See what else is going on. What about these? You guys must have seen this. Okay. Close. Get real. Get real. Get real, man. I had a student say that to me last semester. I thought it was like the best thing I've ever heard. Get real, Dr. Kerr. Like, all right. Anyway. This, real numbers will satisfy, you can get equations like this, right? That you can't solve for like rationals. What's the solution to this equation? Nope. You try. Ooh. What's that thing called? Radical? Skateboarder? Huh? Square root of 2. That's right. Square root of 2. Radicals. I got it. Square root of 2 will satisfy that. That's a real number, but not a rational number. It is irrational. It is irrational, but the reals also contain the rationals as well. So it's not just irrational. I can't seem to draw. What about this one? You guys all stop at real? What?
Imaginary? Is that imaginary?
This guy, he has a lot of vocabulary. It's very impressive. However, it is, you're like, you've got some of you, you're like partially right each time. So hey, that's better than 0. It's better than 0. So the imaginaries are in this, just like the irrationals were in the reals, but they're not the only ones. complex numbers. Class is basic. Let me tell you something about that. Okay, but they will, you can solve an equation that you couldn't solve before, right? Now, this is something math does actually, by the way. It's not just with numbers, it's with all sorts of things. It's we create a world in this case of numbers, and we hit a problem that we'd like to solve, and we realize there's no solution. So we create a bigger world. It's like something we do. We're doing it for hundreds of years, still doing it. Now, when you get up to this level in this world, back in 1843, you know, Hamilton noticed, and many mathematicians noticed something about all these systems, which is that in all of these systems, there's an equation that holds no matter what number you choose, two numbers you choose. But you multiply them, you can switch the order and you get the same thing. Commutativity. You guys probably learned that in elementary school or something. Forgot it promptly after. The way of things. However, Hamilton didn't forget. He got drunk one night and he walked down to a bridge and he wrote these equations and defined, that's okay, quaternions, which expand the complex number system from a two-dimensional real system to a four-dimensional real system, where now you do not have to satisfy this equation. In fact, in this, there are two new numbers, J and K, in here, and I'm not joking that this is true. These, you may say, okay, well, that sounds like a ridiculous story, and it is. However, this number system is used extensively for all of you. I don't know how many of you play video games. Doesn't matter to me. But if you go and play video games, the way many video games graphics are processed quickly from a point of view of whatever avatar you're controlling is using quaternions. It's a very efficient way of doing change of coordinates in 3 dimensions or 4 dimensions. This actually has quite a bit of applications in computer science. If you ever do programming for a computer, for video games. But there's other applications. Satellites, things like that. All right. So I thought I'd share that story because Hamilton didn't just do that. He did some other things. Actually did, as I said, he did quite a few, had quite a few wonderful ideas in very different areas. And one of the areas that we're talking about today is graph theory. And I'm going to talk about Hamilton paths and circuits. I want you to be aware that the book uses this notation, vocabulary. I've seen Hamiltonian paths used, that word, and Hamiltonian cycles used. So you might, if you ever run across this again, you might see those words. I actually kind of prefer Hamilton paths and circuits because there is another completely different structure called a Hamiltonian that has nothing to do with this. So I think it does. Anyway, so what were these? Let me remind everybody. So given a graph, this guy, this is a path. Which visits each vertex exactly once. And then a circuit. This is a circuit that does the same thing, but you have to be a little careful, I guess. The circuit which visits each vertex exactly once. I think I'll say that and then I'll explain the words. So you come back to where you start, but you consider that as, I mean, just having visited it once, I guess. Maybe you don't consider where you start a place you visited, then come back to it. Does that make sense? If I cycle around, I'm going to visit each vertex once, but I'm going to come back to where I start. I'm not going to consider visiting that twice then. It's just a cycle. Sorry. You'll look at an example. So let's look at a few examples and try to get a distinction between the Euler paths of circuits and Hamilton paths of circuits. Different ideas. So start with just a real basic example. Let's just do this. So I'll go. A little graph that looks like this. So I'm going to ask you guys, is there an Euler path, Euler circuit, is there a Hamilton path, for this graph? What do people say about Euler path? Is there an Euler path in this graph? No. Why not?
Because it's not exactly two vertices.
Very good. That's perfect. Yep. So we have theorems that tell us when these exist, right? And so there's no, as was just mentioned, there's no Euler path. So we'll just say no. Euler circuit? Yes, there is. Someone else want to say why there is an Euler circuit? All have degree 2. Very good. So all even. How about a Hamilton path? Yes. By the Hamilton path, we can just start, say, at A and go alphabetically to E, right? That'll give us the Hamilton path. How about a Hamilton circuit? Yes. Just same thing, but then end back at A again. So this graph has 3 out of 4, which isn't bad because you know that you can't have, cannot have both of these at the same time. I did this one. Sure. So I look at the graph. So one place you can get a lot of graphs is you can take a polytope, a 3-dimensional solid, polygons as faces, and you can look at the edges of it and vertices. That'll give you a graph. I did this. This is, who knows? Wait, did I just say what it was? Who knows what this is? This polytope has a special name. Who knows what that special name is? 3D diamond. And that's a lot nicer sounding than the actual name.
A triangular prism.
Not quite.
Is some
Wrong. Something wrong. Yeah, I think all this is like that. I didn't know. All right, guys. So. Octahedron, you're looking that up? Is it good? Or did you listen? Is it good?
Yeah.
This is an octahedron. That's true. Very good. 6 years ago. Has anyone ever heard of an octahedron? Yeah.
6 years ago.
6 years ago?
5 years ago.
That's good. Did you hear of anything else 5 years ago?
I don't remember it.
You got-
Yeah,
Yeah.
I've run to the bill a few times since then.
Yeah, okay, yeah. Onto the bridge. All right, yeah, so okay, so octahedrons have a story. There's a lot of stories. I like stories. Sorry if you guys know. You know what that one is? That's not an octahedron. This one.
Oh, that's a pyramid.
Pyramid. It's not an unreasonable thing to say. I mean, it's a pyramid. I'm not drawing it to scale, but it is sort of a pure. Usually pyramids have a square base. This is a triangle base, but you could call it a pyramid if you had allowed different bases. This is known as a tetrahedron. And then there's another thing. Okay, you guys are all going to know this one. Yeah, there you go. Look at that. You before I finish. This is a cube. And then there are two more. Two more that have perfect, like have regular symmetries where all the vertices look alike and all the facets look alike. You know, anyone, well, you guys didn't know. No. There's the icosahedron and the dodecahedron. I won't draw those because I'm not good enough to draw those. But you can look them up. And these guys, I don't know how to spell it, dodec. Yeah. So these 5 guys are known as the Platonic solids. As Plato and his crew, they knew all about these guys. There's a long history because I mean it goes to the Greek, right? Long history of these. They thought these were mysterious. They like conflated them with like the fundamental, pieces of matter, earth and wind, all that kind of nonsense, right? They believed in that stuff. Kepler, even later on, much later, right? Thousands of years later, thought that these governed the planetary motions, these shapes. And in fact, the Greeks, they like believed that icosahedron was like really special and that it shouldn't be shared with the masses. Like people shouldn't see it because it was too cool or something. I don't know. It was like, their brains would explode. Anyway, these mathematically have a lot of very interesting properties. And there are more modern mathematical things you can say using these, but I don't want to get that. Now, if we look at this graph, what I did want to do is I wanted to look at this graph, the octahedron, and ask the same question that we had before. Same set of questions. Do we have an Euler path? Do we have an Euler circuit? So now everybody, especially those that are very quiet and shy, will answer. We have an Euler path. And I'll shout it out at once. Don't all shout it out. You can shout it out. Does everyone agree? No. He's usually right. Yeah, see, this is the thing. This is why my smart kids are the worst. I was telling my daughter this just yesterday. She's not the worst, but she can be. She was like, my teacher never calls on me and I raise my hand all the time. And I'm like, lady, you're raising your hand all the time. Put your hand, chill. Let other people have a chance. I don't know if she'll listen to me at all.
It's probably a yes because you didn't like the answer.
Okay, see, now that's also, you're gaming the system. What about learning the subject? All right, guys, I understand what you're saying. Like, these are all, come on, not every test needs to be guessed, right? We don't need to guess the answer. Huh?
What's the verdict?
Euler path. Help me out, guys. Euler path.
Even.
No, I've got 2 no's from the smart ones. I've got a gamer over here. Figure out the odds based on my expression. How many edges, what's the degree of this vertex? 4. Now, if you look at an octahedron, what I just said, what's so special about these shapes is that all of the vertices look alike. Right? These have complete symmetry. Like you can, so all of the vertices have degree 4. So they're all even. Now, if we want an Euler path, what do we need? 2 odd, exactly 2 odd. Do we have them? No, we don't. Thank you. Good. So no. So the smart ones were right. Your initial guesses based on secondary information was correct. Okay. What about an Euler circuit from someone over in that far reaches of the? Yes. Yes. Because? Shh. Stop. Huh? Not you. You're good. Just because? Just because. Because of the whisper.
I mean, you have a 50-50 chance here.
You don't have a 50. You mean a 50.
They all have the even.
They all have it very good. They're all even. All the vertices are even. We say a vertex is even when its degree is even. Great, guys. All right, now Euler was great, and Euler's theorems are great because you don't have to think very much. You just have to look at the vertices and ask whether they're all even or odd. Hamilton paths of circuits can be harder. There's not like that easy test. So there you have to look a little bit and see if you can find one. If you can find a circuit, Hamilton circuit, you can definitely find a Hamilton path. You just chop off one of the parts of your journey. The converse is not true, and we'll see that. We'll also ask what that is. Is there a Hamilton circuit? Let me ask this question first. What do you guys think? Yeah? You say yes. Okay. Okay. How many people agree? How many people say yes, guess yes? I'm just asking for a guess here now, so no commitment.
Sure.
I won't call on you and ask. How many people say no? Guess no. No opinion. How many people have no opinion? Don't raise your hand because Okay. No opinion is correct. No, I'm just kidding. It is yes. It is yes, right? And there are a lot of them actually. So if we want, we can do something like this. There's a path. That's a Hamilton circuit. For example, I visited every vertex exactly once,
I didn't think of it.
right?
Every single line.
So good. Okay, so this is right. For someone's okay. You're saying you're thinking every single line. That's what this is, right? That's the Euler circuit. You visit every edge once. That's the Euler circuit, and you can visit a vertex multiple times with an Euler circuit. That's fine. But Hamilton circuits are different, very different. Just you want to visit each vertex exactly once. They are much harder to deal with in general. Like not a little, a lot. So these are harder. Hamilton. Okay, so there is both of these. So now we've seen two examples where we have the same set of answers. Let's take a look at one more where we don't. So let me say. I don't know, do this graph. I don't know if this has a name or not, I don't know. Let's ask the same questions. Okay, so for Euler path.
Oh, you're asking.
Yeah, Euler path. Sorry, let me be more clear. How many? Who thinks there's an Euler path? Nobody. You guys are all geniuses. So you haven't looked at it. That's why I was trying to rush in and say you. I don't want to See, actually, never mind. All right, so all of them are odd. Pretty odd. Too many odd. So no Euler path because there's too many odd guys. No Euler circuit, same. I mean, if you have one odd vertex, there's no Euler circuit. Hamilton path. Yes, I've got no. I heard a no. Not a circuit, path. Hamilton path. Let's check it out. Here's one example of a Hamilton path. Right. I can do that. And now, so there is a Hamilton path. Hamilton circuit. No, there's no Hamilton circuit. Now, why? We don't have a theorem to appeal to here. What could you say that would be very convincing about why there's no circuit?
Sorry, are you on in? It's hard to get back to where you started.
Okay, I agree. That's good. Yeah, what's some other ideas here? I like that. Now we got some vocabulary in the house. I love it. What were you gonna say?
I was gonna say two bridges.
Yeah, you've got some bridges. If you've got a bridge, so let's say I have a bridge and I have some part of the graph over here and some part of the graph over here. Remember, a bridge is something that if you get rid of it, you've disconnected, right? If I have any bridge, I cannot have a Hamilton circuit, right? Because if I start over here, I go around, once I cross that bridge, how am I going to come back? I can't, not without hitting the same vertex again. So the existence of a single bridge means there's no Hamilton circuit. So that's a nice fact to keep in mind if you're looking for these solutions to these problems. The graph has a bridge. And it does not have a Hamilton circuit. It might have a Hamilton path. Okay, now I'm going to ask you guys a question. Ask you two questions. First question is the second question. Well, first, the question I'm writing is the second question. Is the converse true? That is the second question I want to ask you guys. The first question I want to ask you guys is, what does the converse mean? Okay, good, right. So these are mathy terms. However, they're not just mathy terms. They also appear in like sophisticated comedy shows. Like, South Park or something. I don't know, like, I mean, comedians love using transitive property and converse and all that stuff. But they also will appear, I overheard as I was getting set up, someone's going to law school or something, maybe not to law school, pre-law. They will definitely appear in any kind of law school, right? Any kind of debate, any kind of thing. Basic logical terms appear all the time. If I have a statement, what does it mean to talk about the converse of statement? Okay, let me give an example. Here's a statement. If I do not drink coffee, I go crazy. What is the converse of that statement? If I go crazy, then I did not drink coffee. That's the converse. So A implies B is a statement. The converse is B implies A. It's also a nice pair of shoes. If you like that. Christmas sweat. All right. A statement can be true, and the converse can also be true of that statement. A statement can be true, and the converse can be false.
There are possibly other reasons why you're crazy.
Yes, exactly. That's exactly the point, right? There's all kinds of reasons that I'm crazy. Huh? I teach math. Yeah, that's more a symptom than a cause.
Directly math 160.
Right, so. Right, A implies B does not necessarily mean that B implies A is true. So here I have a statement. If a graph has a bridge, then it does not have a Hamilton circuit. What is the converse of that statement? If a graph does not have, I'm sorry, I asked the question. I'll just answer it though. If a graph does not have a Hamilton circuit, then it has. So this is the converse of the fact. The question is this converse true or not? I mean, let me give you a more simple example than the crazy coffee example, right? If I am a tree, I have a trunk. That's a bad example. If I wanted to say leaves, because I mean, do you count needles, pine needles as leaves? I was trying to find something to be correct. Okay, if I'm an oak tree, then I have leaves. If I have leaves, then I'm an oak tree. That's not true, right? So I'm just trying to say you can cook up a lot of examples of statements that are true whose converses are not true. You can also cook up examples where the converse is true. So this is knowing that something's true. I'm trying to really make the impression. Knowing something is true does not mean anything about its converse. You have to look at it separately. So even though this is a fact, this is a different question. Now, the answer to this question is not something I'd expect you guys to, well, I'd be impressed, very impressed, if you just rattle off a correct, well-argued, well-reasoned response here. Converse in this case is false. There are examples of graphs that have no Hamiltonian circuit and no bridges. Here's an example. Beautiful graph that actually has appeared in research of one of my graduate students a couple of years ago. called Peterson graph. Very interesting graph. Kind of weird. So here I'm drawing edges, but the crossings are not vertices, just the edges. So it has 10 vertices. It has these 5, and then the outer 5. And you can show that there's no bridges here. This is a very symmetric graph. And you can also show that there are no Hamilton circuits. If you want to try, what you can do is you can say, well, if there was a Hamilton circuit, it would have to go from this inner part to the outer part at some point. And it would have to do it an even number of times because you have to start and end on one side or the other. So if you cross over, you have to come back. Cross over again, you have to come back. And then you can look at the cases. At how many crossings. So for example, I'll just give you one kind of argument here. I won't do the whole thing. If you cross twice like this, well, sure, you can make it around here. But now you have to go from this vertex to this vertex, hitting all the other 3. So you only have, let's say we're starting here. We have 2 choices. We can go this way, or we can go along the other edge. If we go this way, we only have sort of one choice since we have to stay in this inner part, and it gives us that. We left out these 2 vertices. Go the other way, and it gives us that, and we left out this vertex. So that's one of the arguments. You can kind of go through and check each other. It's a very interesting graph. It really does appear. I mean, I looked it up just to remind myself about it because I remembered that this was a graph that had no Hamilton circuit and had no bridges. But when I looked it up, I saw that there was actually another paper that was just written, a journal about it, using it for very different purposes. It's an interesting graph. Anyway. Converse is not true. This is false. But this kind of shows you that things can get pretty dicey with Hamilton cycles and paths. It's not like Euler. It's not as easy. And knowing when something has one or not can be a bit of a journey. But there's some theorems, it's just we haven't found. All right, so what else? So we'll want to know some graphs, and some graphs occur a lot and are sort of the universal graphs, the ones that we would have to deal with if we had full information in some cases. And so let's talk about complete graphs. They have notation case of n. Here n is the number of vertices. I'm going to draw the first few. The first graph, okay, if n is 1, n is just a vertex, nothing to it, right? One vertex. N is 2, the 2 vertices, and we have the edge connecting. N is 3 vertices. And the point of the complete graph is that every 2 edges are connected exactly once, no loops. Four, well, I just drew this picture for 4. This is indeed the graph associated with the edges of a tetrahedron. To draw it that way, another way you can do it is kind of look down, top down, and kind of put something in the middle. This is another drawing of the same kind of graph. You don't want edges to cross each other. Sometimes you can draw a graph so that none of the edges ever cross, and sometimes you can't. In this case, you can, but not always. In the case of the complete graph K5, you can't do this anymore. You have to cross lines. So if we just say through pentagon, we have 5 vertices. Well, then we kind of connect the outer vertices. Then we have to connect. So again, the crossings here, they don't indicate new vertices. I'm just drawing the edges between. Does that make sense? People have questions. These are called complete graphs. That's their notation. But write that down, or if you see that in the homework or in an exam or whatever, you'll know what it is. Yeah. I wrote down K11. What would it mean to you?
11 vertices.
And all edges, right? All of the edges. Good. Now, complete graph. Graphs have Hamiltonian paths. And circuits. Okay, assuming here you need for the circuit case, we need this case, we need n greater than or equal, well, greater than 2. So, I mean, if we just look, it's not hard to see, right? Here's a Hamiltonian path, here's a path, here's a path, right? We find a lot. So now, furthermore, we can actually count them. That's kind of an interesting question. How many? The paths. Hamiltonian paths. I'm going to say Hamiltonian sometimes. I'm sorry, but Hamilton. I'll try to remember. How many Hamilton paths on? Let's say K3. So let me draw K3. I'll label the vertices. What do you think? Okay, I've got 3. I've got 2 people that guessed very quietly. 3. 3.
Yes. Go for it.
I mean, you might be right. You might be right. It depends on what you're thinking. I have to clarify what you're thinking. I will say that there's 6.
Oh, because you're reversing.
Right. There you go. Good. So right. So you can say a path for me is I start somewhere and I go somewhere, right? If I said I was on my way to school today to teach my class, I left my office, I left the classroom at 3 o'clock. That wouldn't make any sense, right? Because that means I'm going back from school, not to school. So the direction of a path is differentiates it. So I have 6 because I can write them down and I won't put commas. A, B, C, A, C, B, B, A, C, B, C, A, B. There, I wrote all 6 of them down. When I write them down like that, does anyone know what these kind of ordered things are called? Ordered words, of letters are called. Okay. Huh? There's another word. I'm sorry. What? Yeah, you'll know it when you hear it, right? So. Nobody knows? Pattern. Good. Guys. It's a class of forgetful. I can see that the high school education system really pounded in a lot of these words. These are also, okay, you'll know these, right? These are called permutations. You remember permutations?
No. And what class do you learn that in?
Like
geometry?
six, if you look at Common Core math, I promise it's like 6, like discrete math maybe? Like, or whatever like version of that is,
Yeah, I was
algebra?
like, I remember learning that, but I was like, that could have been like.
No, you have
7
horrible
years ago.
teachers. I don't blame you. It's not your fault. Their teachers were the worst.
It's like, it might have been, it's been 4 years since I've taken math. So.
I know, but you should remember this because they should have been. Anyway, okay, so guys, we'll talk about permutations next time. That will come up later in statistics and probability as well. So when we talk about that.
For online.
I was like, all right,